Right, so continuity, in other words, is a graph continuous or not? Okay, very simply, a graph is continuous if you can draw without lifting a pen from the piece of paper. Okay, if you can't, then there will be discontinuous, and there are different types of discontinuity. So fundamentally, discontinuity is due to the nature of the graph. So there's hyperbola. So you can't actually draw this graph without taking your pen off the paper. It's the nature of the function. The other one is the fact that there is a hole in the function. So you have to take, to do it properly, you have to take your pen off the paper. And the other one, there is a jump. Okay, this jump, that's your piecewise. Okay, so there are those types of continuity. Now, that is one part. The other part you need to be aware of is this differentiability. Okay, so a function is differentiable if the derived function is defined at a point. This may be confusing as it made it sound. So, in other words, the graph, for it to be differentiable, the graph must be smooth. There can't be any sharp corners. So, if there is a sharp corner, then the function is not differentiable at that point. And there mustn't be any non-vertical tangents at the point. So in other words, here are some graphs there. Below are the functions, below are the gradient functions of the graph. Okay, and as you can see here, if I drew the gradient function for the first part, there would be my gradient function there. For the second part, there would be my gradient function. Because there is a jump here, it is not differentiable at that point. So I cannot derive this function at that point. Again there, this gradient has a vertical tangent along here, so I cannot differentiate it there. It is not differentiable. I struggle with some of this English, FYI. Another point here, so this function has a gradient of a number, and then all of a sudden the gradient function jumps down there. And again, this jump means it's not differentiable at that point. Okay, so there are lots of different types of functions. Okay, so many functions are differentiable not just at points, sharp corners, vertical tangents. So just get your head around that. If a function is not continuous, it is also not differentiable. If a function is differentiable, it implies it is continuous. Okay, so if you look at some of these old exam questions, okay, we had a quick look at that before. In fact, there are the answers from before. Where is a function not differentiable? Okay, so where there are points of discontinuity, where there are sharp corners. So there is 1, 2, 3. Are there any more points of not differentiable? Let's have a look back at our stuff. So are there any smooth? Yeah, that sounds about right, eh? Okay. So that's discontinuity, continuity, differentiability, not differentiability. The last one I wanted to look at was this idea about the concavity of a graph. Okay, so you should sort of be able to remember that from last year, that here is our function, this black line is our function over here. Okay, here is a local minimum, there's a local maximum. The function is decreasing from here to here. It's actually increasing from there to there, and it decreases beyond there again. If I was to draw the gradient function of that, this gradient function would be here's my gradient function. It would be decreasing, and then all of a sudden it'll start increasing again. It's this point here we call this the point of inflection. Okay, that is the turning point of the gradient function. It is where the concavity changes. What is this concavity stuff you talk about? It's basically where the gradient function of the gradient function is if it is greater than 0 or it is less than 0. If the gradient function of the gradient function, in other words, f dash dash x, is greater than 0, then it would be like a bowl. Okay, I'll get a pen. It could be like a bowl. So here is where the gradient function of the gradient function to about there, where that is greater than 0. Okay. Now, if you notice, if the f dash dash is greater than 0, it means the turning point will be a minimum. And that is a test that you will do later on. Okay, if you differentiate a second time and substitute a value in, if it's greater than 0, it is concave up. Therefore, it is a local minimum. Next one here, all along, try to get a fat pen, but it didn't work. There, that stuff there is like an umbrella. Now this point in the middle here, I've just tried to guess. I'm not saying it is exactly that point. Okay, I've just tried to guess, but that is where my second derivative is less than 0. Second derivative less than 0 means I've got a local maximum. Okay, second derivative less than 0 means it's a concave down graph, which means water would run off like an umbrella. Okay, so there are a few key points there. Second derivative helps to identify points of inflection because you can solve it to be equal to 0. It also tells us if it's concave or concave up or concave down, which therefore will tell us if it's a local maximum or a local minimum. Okay, so a real quick overview about that stuff. So have a pause and have a crack at some of those questions, and have a look at some old exam questions. So, hold on. First of all, let's answer these ones. So, where is this one? Where is the f dash x equals 0? Just there. Is that the only place? We'll assume so. We'll go with that. Could be other options. And where is the f dash dash x less than 0, which suggests a local maximum? It suggests some sort of umbrella. I'm thinking it's this part just here. So we're going to say x is greater than 3. Okay. Hopefully that makes sense. Hopefully I got those right to start off with, but have a crack at some of those questions that are on that sheet now. Okay, and if there are any questions, make sure you join the team chat and ask.